Okay. Good morning, everybody. So it's a pleasure to start today's lecture with Professor İnanç Adagideli. He doesn't need a long introduction. You already know him. He has been doing lectures previously as well. But just a couple of words. İnanç Adagideli graduated from Middle East Technical University, PS and MS. Then he got his PhD degree from University of Illinois Urbana-Champaign. Later he joined the Sabancı University, and he has been quite active along these topological materials and so on. He's a fellow of the Bilim Akademisi, and he is the senior researcher at the TÜBİTAK Temel Bilimler Araştırma Enstitüsü as well. Today, he will talk about quantum dynamics and computation at the topological edge. It's our pleasure to have İnanç. Please.
Thank you so much, Oğuz, for the kind introduction. So let me start sharing my screen. Hold on 1 second. Need 2 seconds more. Okay. Okay, so could you see my screen now? Let me just start the slideshow.
Yes. This
all good. Great. Excellent. So could you also see my cursor, or shall I make it?
Yeah, it's moving around, yes.
Okay, great. So let me just see laser pointer, maybe, but that might end up not so good, but we'll see. Let me just use, no, that's not a good idea. So I did something really stupid. Hold on. Okay, good. Now, welcome everybody. So I will be talking about, this is again, good. Today I'll be talking about quantum dynamics and computation at the topological edge, but in particular, I'm going to be talking about something particular. You all remember from last week's talks that, you know, I'm of course interested in this topological edge states and then how to use them in computation. And you realize that, you know, we also discussed how you can do the kind of the rudiments of topological computation. What we usually need is these things called Majorana zero modes and so on. And for that, we need a superconductor at the same point where there's a topological edge. So now what you need is a topological superconductor. Of course, there are various ways that people trying to achieve this with proximity effects and magnetic fields and so on. So those are the general theme. But then, of course, you know, what better way to actually imitate the kind of the original topological insulator. The original topological insulator was the quantum Hall state, right? So this integer quantum Hall state is the original topological insulator. We didn't name it such because we thought that was a unique thing. But then we realized actually there came a huge based entire classes of topological insulators. So now the important thing is that you know, we want to ask the question in this lecture, or if in this talk, that, you know, can you actually have a Landau level? Remember the quantum Hall corresponding quantum Hall state for a topological superconductor, which then be a topological superconductor. Now the thing is that, of course, therefore, what we need, as you remember from your maybe from your condensed matter and quantum mechanics lectures, in order to be able to get a quantum Hall state, what you need is Landau levels. Right, those Landau levels ultimately bend and then form these nice edge states whenever you have a high enough magnetic field. So now, therefore, let me just, I'm going to stop this, if I may. Let's see if I can do this. Okay, good. So now today, so I will be talking about basically Majorana Landau levels. So this was actually a fun project. So this is something that we have been working on for quite some time. And finally, you know, this is the latest. And actually and it actually got the lottery for the pretty picture for physical review letters. So we made it to the cover. So this is the first time in my life. Of course, it's nothing, nothing big, but it's kind of nice to see this nice PRL cover with the nice picture, something that you worked on it. And what you see here is basically it's the signature of this minor lambda level. The answer would be yes. So to give you a hint from the end of the talk. Good. So this is work done in collaboration with people in Leiden. Michał Pacholski is the hero of the story. He is a joint PhD student with myself and Carlo Beinacker. He now graduated and he will be going to Dresden as a postdoc. And Gal and Omri Gal Lemut was still a student, and Omri is a postdoc at the time. So now let me just start from lambda levels. Of course, you all remember your quantum mechanics courses. Here it is, David Griffiths. Griffith's book. So you remember that you have a Hamiltonian, which is our usual free Hamiltonian, p squared over 2m. You turn the magnetic field. You do that by basically adding a gauge potential, based gauge vector potential A. So now let me, how do you really, this thing is not working, so let me try to do this. Okay, I'm going to stop this laser pointer business. Great. So now, now the important thing is that when you solve this, you realize that, of course, the movement, the kinetic energy in the direction of the magnetic field, let's just assume that's in the z direction, won't be affected, right? So you will still have your, kinetic energy corresponding to the z direction will remain the same, p z squared over 2m. But then instead of having those nice free particle based quadratic dispersion in the direction perpendicular to the magnetic field, instead you have flat bands. And those are the telltale signs. These are the lambda levels, and these are crucial for getting basically your quantum Hall state, because you want to tune, for instance, your system chemical potential between them and so on. That's the way you get quantum Hall state. But then you have this famous thing that looks exactly like a harmonic potential. You have this energy that goes with h bar omega c, cyclotron rate frequency, and then you have n+1. And this is the famous energy spectrum for a harmonic oscillator. And this basically remains your energy spectrum for all the kinetic energy corresponding to the directions perpendicular to the magnetic field. Now, okay, so lambda levels in superconductors. So that's the thing. We were not the first one to come up with the idea. Actually, this has been around for a long time. But of course, you realize the superconductors are gapped quasi-particle insulators. So that's why normal superconductors was never really a big thing. But then at the time, there were like these three basically masters of physics, not masters of science, but like basically grandmasters maybe. I usually ask people if they remember these faces. But since it's an online talk, they from left to right, they basically Gorkov, Schrieffer, and Anderson. They really are all not only that really well known in condensed matter physics, but also in the theory of superconductivity. Schrieffer, my fellow UFI grad, did this basically as his PhD. He did the theory of superconductivity. Anderson needs no introduction, and Gorkov obviously also needs no introduction in this case. Now, and at the time, you had this so-called high-T superconductors, which actually had nodal quasi-particles. So your spectra of a high-T superconductor would basically have quasi-particles. They won't be gapped. And they said, okay, so we have nodal quasi-particles with linear dispersion. So then you would actually have lambda levels. And this is from a preprint from Anderson, from, dated 3rd of December, 1998, a decade before graphene was ever uttered. And they kind of calculated this, basically they uttered this really nice relativistic dispersion levels for lambda levels. So instead of having this n+1/2, you have square root of n. Okay, so that was the thing. That was from Anderson, but you never heard of this, and this paper was never being published because it was actually the first time relativistic lambda levels maybe appeared in this real condensed matter context. And if it had been observed, this would have actually you would have been all aware of that. This would have been a decade before observation of lambda levels in a condensed matter context, relativistic lambda levels. But it turns out this is not the case. So now I want to say that you see that this is a superconductor, so put a magnetic field. Superconductor strongly repels magnetic field. So usually what happens is that you want to be in this, for technical part of this talk, you have to be in this so-called limit where you are actually in between the two critical fields, so that, you know, you have to be high enough magnetic field so you can actually start penetrating the flux lines into the superconductor, but not enough yet go to the level that, you know, that this is all completely destroys the superconductivity. Right? So typically in that case, you actually have a vortex lattice, right? So, but then that vortex lattice, that was the reason this didn't work, this didn't fly, was actually shown by the first time in '99, exactly, basically maybe in a couple of months, by Melnikov, saying that that vortex lattice would actually strongly scatter the quasi-particles. You won't be able to actually see this nice little flat bands, because that nice flatness would be destroyed by the vortex lattice. And in fact, within a year, Franz and Tessanovich came and, you know, also went on this problem. In fact, it is maybe the first ticket to fame for Marcel Franz, that they said basically Melnikov is correct. And in fact, if you look at this lattice, you would find out that you actually have Bloch spectrum. It looks like you actually even see a Dirac cone. That Dirac cone does not disappear, but just gets renormalized velocity. So then, you know, that was it for the Landau levels in superconductors. And here it is, that's what it means. So this is a spectra for a D-wave superconductor. The vortex lattice strongly scatters the quasi-particles, means that basically instead of having these nice flat bands, you have these, so the dotted black lines are the original D-wave spectra. And what you see here is basically the lines for, you know, they got flattened actually. You might even say that, you know, basically with a lower's eye, you might say that these are actually Landau levels, right? So you see the 0th one, the first one, the second one, and so on. But, you know, they got strongly scattered and they formed actually Bloch waves. So in fact, you even exacted the Dirac cone, that cone is even retained. So you cannot really use this as a topological superconductor. There it is. So now, after 2 decades, we were interested in this problem. So I was on sabbatical, and, you know, I was trying to think of like stuff that I, you know, heard all along the way that really caught my attention, and tried to solve it. That's the perfect time for sabbatical. And one thing was basis fermion doubling problem, and the second one was this. Basically, they were actually turned out to be related. Because when Marshall Franz got their results, I was a student at Urbana, and it was a big thing. I was really, you know, we were really excited to have a Landau level, and then turned out it didn't work, and so on. So now I was actually turned out that D-wave, right now we of course have all sort of other nodal superconductors, and D-wave at the time was, you know, the one that was available. But now what we had was basically is a Weil superconductor. This is basically, we talked about that last week. These are Weil superconductors. Remember, Weil semimetals are, you basically have this nodal, like a graphene, right? You have a nodal quasi-particles, but then those quasi-particles are now in the Bogoliubov spectrum, right? So you also have superconductivity at the same time. And it turns out, if you have a Weil superconductor, and if you put magnetic field, even in a vortex lattice, it's a very similar system to the D-wave, but it turns out that the Landau level persists. And there is a very important, like nice underlying mathematical reason for that. And that is basically a neat thing called topological protection. So the vortex lattice in the D-wave is not a topologically protected. The states that are formed are not topologically protected. Therefore, they get scattered by the vortex lattice. And in a Weil superconductor, those states get scattered, but those scattering cannot shift their energy. So therefore, you have topological protection. So now, and this is how it looked. So this is the D-wave superconductor. And then you basically have, you know, you saw this kind of Bloch waves. And then if you do this thing in a Weil superconductor, you would see this spectrum. You see that the dotted lines are the basically unperturbed spectrum. So you would basically have, again, this Weil, these are now not the Dirac cones, these are the Weil cones, right? Again, this conic spectrum in the unperturbed state. Now we put the magnetic field. It's a very, you see that unperturbed state looks very similar to D-wave, but, you know, the moment that you actually turn on the magnetic field, you see that very nice flat bands actually are forming. You see that at higher levels, you get that protection doesn't extend. So the protected level is actually the 0th level. The higher levels, actually, you see that there's some tiny bit of basic dispersion, but that actually is very tiny. And even the first and second excited, the first and second lambda levels are pretty flat. So this was then, published at the time. We were really excited. So then came the problem that, there is no wild superconductor. So now you could actually come up with, with kind of the slice structures and things, but then, it's not an immediately available thing. So we kept looking for available physical platforms, right? So that's the thing. So now one thing is that, of course, in topological superconductors in general, right? So we don't maybe need a wild superconductor, but maybe we need a topological superconductor. But the problem is that, of course, topological superconductors are also gapped, right? So we don't want a gap because we want quasi-particles at Fermi level. So, even if it is a nodal one, so to be able to get those lambda levels. So it seems to be a back to square one thing, but the main thing that we need if you want a real applicable physical platform for the topological superconductors, because there are now people who are now working on these, you need basically a so-called Bogoliubov Fermi surface. I will tell you in a second, but what it is basically it's like a Fermi surface, right? We know what a Fermi surface is. It's in a metal. That surface disappears normally in a superconductor because we have a gap. But then in this, you can have a situation where actually some of that surface it remains, right? So there's a kind of a surface still left over. But then remember, in a superconductor, you would have particles and holes, and the general rules of like forming the Fermi surface does not apply. I will show you an example immediately, or actually this is the one. And here it is actually also how it works. So the Bogoliubov Fermi surface, you can actually do this by basically closing the gap in a certain direction. And what you can do, how you can do this, is basically applying a supercurrent. So when you apply a supercurrent, so this is basically the idea from Wolowick, that you can actually, you of course shift the energies of your particles. In the business, it's called the Doppler shift. Of course, because you also basically have a very similar form. And it basically tells you that the energy would be proportional to your velocity in that momentum direction times the superfluid velocity, right? So this is a very directional thing, and it actually can shift some of the energies down. And if you shift it down enough, you basically can actually start having quasi-particles at the Fermi level. Now this goes with with basically starting from this picture, right? This is the superfluid velocity, superfluid density. And then you basically start putting your basically superfluid velocity. Then you keep on doing this. Nothing much is affected. You start carrying supercurrent. But at some point, you actually can have a situation after this critical level of this superfluid velocity. You might start having the superconductor with a Fermi surface before you destroy the superconductivity. Right? So that was the critical thing. And actually, this was taken by people who now basically published in Science in 2021. They basically did this in a very nice setup. And that setup is basically bismuth telluride. That bismuth telluride, for those of you who doesn't know, is a topological insulator. You put it on an niobium selenide, right? So it's a bulk superconductor. Now, what you do is that you apply magnetic field, and that magnetic field basically generates a supercurrent perpendicular to it, right? In this case, that is the superfluid flow direction is PS vector, right? When you apply magnetic field that way. Now that way you can actually, now at the surface between the bismuth and the niobium, right? So that's at the surface, you basically have the topological edge states that get proximatized by the superconductor, forming essentially something you can say that it's basically proximity induced topological superconductor. And then what you do is that you apply this superfluid velocity, and that superfluid velocity would give you the Doppler shift, right? So here the key thing is that this picture that you want to apply enough superfluid velocity, right? So that but then you cannot apply too much because you would destroy the superconductivity and so on. Actually, with this neat setup, it actually doesn't apply because niobium remember, is a strong superconductor. So he actually has a high critical field that, you won't be destroyed by the magnetic field and passing enough supercurrents. But at the same time, you actually have this induced superconductivity at the bismuth telluride piece, which is a weaker superconductivity. So it actually can get to a point where you start having the Fermi surface, Bogoliubov Fermi surface, and so on. So now I want to show you how the Bogoliubov Fermi surface hopefully looks like again here. So this is the picture. So you see that normally in a normal Fermi surface, we would see only the basically, let's say the blue lines are electron lines. In a normal Fermi surface, you would have basically a closed Fermi surface. You would have for pockets and things, and they would all have to be connected. But now remember that connectivity doesn't extend to superconductors. You only have to connect the entire quasi-particles, but the entire quasi-particles might actually have an electron or a hole character. Remember, this is the superconducting hole character, not the semiconductor hole character. So which means that basically it is the absence of the electrons. So you basically have a Fermi surface when you talk about the real thing. You basically have a disconnected blue Fermi surface, and then the red one is just basically the particle hole counterpart to that. So that total thing is connected, but if you're looking at, let's say, if you're just probing electrons, let's say with a with ARPAS or something like, something more like a local probe, like a STS probe, then you would basically at a certain thing, you would start probing the electronic part. And that would actually, you would only see the blue part. So you will see a disconnected, real Fermi surface will be disconnected. And that is a telltale sign of this. So now here is what they saw. So you basically at B equals to 0. So this is basically a method by at the time, again, coming back from the high TC days, that you basically have a scanning tunneling spectroscopy on the surface. The data that you get is a local density of states. And then that's local density is a function of position. You Fourier transform that, the experimental data, to get your density of states in momentum space, or the spectral function. And that would actually have data about how stuff looks in your momentum space. And indeed, you would see that at B equals to 0, you basically have a gap, so that you don't see anything, you don't see any structure. And as you increase, as you increase the energy, you would start seeing the quasi-particle states at, when you're biasing at -2 millivolts. These are basically the Dirac cones, but at that level, you get this so-called this hexagonal warping effects. So that's why actually it should be, in a very smooth thing at lower energy. This will look very circle-like, but at higher energies, you will see this hexagonal stuff. And then you basically actually can get the same, basically a directional version of the same picture whenever you apply magnetic field in the direction perpendicular to the magnetic field, and at 0 energy, you would start seeing this signatures of quasi-particles at 0 bias. And those are basically the Bogoliubov Fermi surface. Now the question is, can I actually, use my formalism and everything? Can I get Landau levels in that system? Because this system is already there, people can work on this and so on. So that's what I'm gonna basically talk about. And that's, I'm gonna spend the next few minutes on that to give you the answers, and then we will have a part that we will discuss how that actually comes to be. So now what happens is that basically you have this topological insulator, and that's on top of a superconductor. That's the system that was basically done by the experimentalists. And now you actually have, you have two magnetic fields, right? You of course have to have magnetic field because you have a superflow. You can of course have some other ways of inducing superflow. You don't have to put a magnetic field, but now you have to put a magnetic field on top of this, and that presumably would form in a vortex array. And then you with that thing, you might want to see what happens to the energy levels and so on. So now actually this is a well-known system, right? Without the superflow, we all know that without the superflow, this is basically so-called the Foucault structure. You basically have a topological, you basically have a vortex on top of a, superconducting vortex on top of a topological insulator that binds Majorana 0 mode. And which is really cool because these are the modes that we want to manipulate actually. So now what you see when you turn on the superflow is that you see, this is from simulations. You see that the superflow, right? These are basically localized modes that are here that actually are spherically symmetric. You see that the superflow blows on the Majoranas, right? So remember the superflow is in that direction. It's the same directional thing. So the superflow is going, this way. And then you see that the the Majorana modes are blown perpendicular to it. Right? You see some remnants of this thing, you know, this directionality on the Majoranas. So then you might ask yourself that, okay, that's really cool because I can start manipulating these Majoranas with that, basically with some superflow. What actually distinguishes the direction that it blows, and it turns out it is the kind of the spin of the Majoranas that is distinguished by the superflow. If you basically, instead of a vortex that is basically, let's say, +1 vortex, you put a -1 vortex that binds the opposite type of Majoranas. And you see that that's what you see, right? Here's a vortex lattice made out of all up vortices. Here, of course, it's not realistic, but what you see on the right are basically a lattice of up vortex, down vortex, up vortex, and vortex anti-vortex pairs. They bind the opposite Majoranas, and you see that the same flow blows them in the opposite directions. So now that's really, really cool. But now here comes the, let me see. So now just close this smaller. So you basically, you can actually distinguish the spin of the Majoranas, which is really cool because remember we were talking about, we started when I was discussing the Majoranas from a state which was basically spinless. That is to say that you basically have a state which actually had let me just see, hold on. So when you see this, you basically, it tells you that, you know, there is, you know, that host fermions would actually start having a certain spin. Now, when you have the certain spin, you basically, you know, but then if you look at the real spin of the Majoranas, you would get zero, right? So you have zero spin, zero energy. It won't shift in chemical potentials. That's the whole point. But if you blow on them with the supercurrent, you can actually blow them in a certain direction. That's actually is actually very exciting thing. So now the question is, this Magnus force distinguishes the spin, right? If you actually strong enough, you put enough force on that. So I'm missing some. It looks like I'm missing some things, but I think maybe on the other hand, this may not be such a. 1 second, let me see if I can. It looks like I am missing. Well, okay, maybe not. Let me just continue on from here. Okay, so when you put enough superflow, and that is the kind of the key thing. So you see that these Majoranas, they go blown away, and then they start seeing the other Majorana, right? So that's the thing. So you can actually, better here, you see that you blow on it too much, you will start seeing the other Majorana. We know that they don't like to be together, they get hybridized and so on. And this is what we thought would happen in the beginning. So if you blow enough of these, and then possibly you would generate again that you know, isolated states would actually disappear, and you would end up getting just our usual you know, our usual, you know, this dispersion relation and you know, blown, like basically hybridized Majoranas. Now, but then this is not what happened. The moment that you do this, you find out that these delocalizes the Majorana zero modes get a delocalization transition, and they form flat bands. And basically, this flat band is basically the zero lambda level we were after. So you basically generate a zero modes. Basically, you know, the Majoranas are, and that's kind of the main thing. And I will go on to explain you how actually this whole thing works mathematically. But before that, these are basically the results from basically the take-home message from the talk, is that you can have Majoranas, and then you can actually, normally you have to have them localized. That's the problem, because you want to manipulate them, right? So you can, of course, take the vortex and then move them around. But this tells you that you can actually delocalize them. So you can actually, hopefully, maybe once they delocalize, you know, and they still keep their Majorana character, right? They don't get, you know, they still, and then they form a Majoranas basically lambda level. As to basically would be the first time if this is observed, this would be the thing. And the telltale sign of this would be these wonderful picture. So if you look at this scanning tunneling spectroscopy, instead of finding those things, you would find a striped picture. And that's basically carries a wave vector, and you'll see that that wave vector actually has a very specific dependence on the induced superconductivity and applied supercurrent. Okay, now I'm gonna so this is basically the final take-home message. So what I'm gonna do now is that I'm going to switch gears and tell you about some methods and how you actually can get this protected Landau levels in this case and not in other cases. And it goes from the method that we're gonna use is something that you remember from your courses. These are the method of gauge transformations, right? So let's just go through this. Right, so this is the Hamiltonian we were looking at from the beginning. You have the free particle, and then you actually then you put this vector potential on it, right? And then p plus a squared over 2n. But if that vector potential is actually is given by some sort of del basically nabla phi, if it is given by the divergence, this is the gradient of another function, right? Then it basically doesn't do anything. We call that a pure gauge. Right. So now if it is a pure gauge, then you basically can show that this Hamiltonian actually is equivalent to a Hamiltonian that had zero field, right? And the transformation that you do is you take that phi, you make a unitary transformation e to the minus I phi, Hamiltonian e to the plus I phi. That's just, you change basically locally the fields, and you get a zero, basically the Hamilton free particle with no field. That's the thing. Now, if you had another term on the other hand, that was something that we learned, is that instead of this being a gradient, this del phi, it actually has some sort of a curl of something else. So basically a z cross del of another function omega, right? In that case, you actually can get rid of phi, but you couldn't get rid of omega. So basically, we say that this function then would have a curl, right? Del close a would be this part that you cannot gauge away, that actually has a field that we call the field strength. That's the magnetic field, Bz, and that's given by this del squared omega. And now, if that part you can actually find out because of this equation, that part that you cannot gauge away, you can write it as basically, remember this is two-dimensional, basically two-dimensional Poisson equation with a source. And that source term is the magnetic field. Then you get this basically Coulomb potential in 2 dimensions logarithm. So you basically just get our old thing from electrostatics to get from your magnetic field the local omega from that. So this way you can actually, even if you wanted to, you can get omega, which will be actually useful in a second. But that part with the omega cannot be gauged away. That's the key thing. So now, if you had a chiral Hamiltonian, that's what we were talking about the last week, is that if you have a Hamiltonian like graphene, sigma dot p, right? This whole thing is in 2 dimensions. This is actually a very special property that the Hamiltonian anti-commutes with sigma z, right? So this has two related basic consequences from this. One thing is that, just like a normal unitary transformation, you can do this so-called chiral gauge transformations. This is e to the sigma z alpha. Remember, those two things have the same sign. And normally you would say that, I was telling this to Carlo, you said, oh, you forgot a sign. So I said, no, because whenever this happens, you can actually take this operator and move it to the other side of Hamiltonian. As it does, sigma z picks up a minus sign because of anti-commutation, and that cancels out the sigma z. So therefore, all Hamiltonian for every constant alpha would have this property. Now, this is a chiral gauge transformation because just like the gauge freedom comes from basically the local phase, like the phase of the wave function is indefinite. So therefore, any Hamiltonian with a local phase choice would be equivalent, right? So if it is so that basically is the previous page thing with a constant phase. Now you actually promote this to a local phase change with this phi of r. So you can actually do that, and we're going to do that in a second. And the second thing that's consequence of this is that you can actually show that you can off-diagonalize your Hamiltonian, just like we did last week. And then this index of this A, right? This is the null space of A minus the dimension of the null space of A, the dimension of the null space of A dagger. would be a topological invariant. That's the topological thing that comes. Now the zero mode comes in like this. So remember, this is the zero mode actually, you know and love from graphene. You can actually, this is basically something like we're rediscovering the wheel here using slightly different notation. Remember that if you have a chiral Hamiltonian, which you can write your vector potential as grad phi plus z cross del omega, and this del squared omega is your B, right? You suppose you solve that, and then you can actually show that, which is an amazing thing, this P plus A, you can actually gauge away the entire A, it looks like, by doing this transformation. And it's basically the same transformation as sigma z omega of R, but then with the same sign on both sides. Then the I phi is the usual unitary transformation. And then you get this P dot P plus A goes to sigma dot P. Now you can say that, well, that sounds really cool, but at the same time, probably we're missing out something. But like, you see that what this tells you is that as operators, this P plus sigma dot P plus A and sigma dot P actually have very related local solutions. Doesn't mean that they have the same identical spectrum. And that comes in when I'm looking at the zero mode. It tells me that if I'm looking at the zero mode of the P plus A Hamiltonian, it will be actually, if the only thing I have to do is that I have to find the zero mode of sigma dot P, which is very simple, right? This F plus and F minus with this simple thing. And then I have to multiply in front of that, this unitary, well, not unitary, but this normal gauge transformation and the chiral gauge transformation prefactor. Now, the key thing here is that, and I think I'm saying it in a second. So in this case, remember, if you have a constant magnetic field, this omega of R is 1/2 BR squared. So your general solution, and you can find the general zero mode solution, is always in this form, minus BR squared over 2 and 0 and F. Right, so that's the key thing. And the only difference, and F is just the local solution for this sigma dot P. Now the important thing here, so then you can actually solve this very simply by looking at any polynomial in the form of x minus iy, or any function looking like kx minus iy. I want the second form because I want to show you that tells you what actually is the key thing about this prefactor. Remember that solution as a solution of sigma dot P won't be permissible because it will be divergent. Only because of this chiral gauge transformation, I have this prefactor e to the b r squared. That term actually heals down this divergence, so therefore makes the normalizable state. Remember, this is the same thing that we got from our earlier lecture last week, and this actually applies directly here. And then you get your perfectly well-known by now zero mode of zero lambda level of the graphene, which then gives you this in Andre Geimster half integer quantum Hall effect, and so on, 2 times the half integer. So and so on. And the number of such modes is given by the index of A. Right? This is something that we know. This is just something we did know and you can, looking at this index, you can find out indeed our usual rules about the degeneracy of the lambda levels and so on. Now, something that is actually directly applicable to graphene. But now we want to apply this to our thing Hamiltonian, and I'm kind of have a little bit of time, so I will just, this is basically the part, you know, like in Nihat Hoca's terms, like this showing under the hood, sort of like how what went into this calculation. So we basically have, this is the confined phase of a topological insulator in based proximity with a superconductor. So what you see is that you see this P minus EA, right? This P dot sigma is your original surface Hamiltonian from the topological insulator. And then you basically have, this is the electron part, and you have the whole part here. And the whole part would feel an exactly opposite magnetic field because that's time versus symmetry odd piece. And then those things are basically hybridized by a gap, but that gap is a complex number and has a phase which winds by 2 pi around each vortex. If it winds by 2 pi, then we call it the vortex. If it winds by minus 2 pi, we call it an anti-vortex. And if it winds by n times that, you call the, basically charge n vortex. That n is a topological charge. Now, the chiral operator here is a little bit hard, but you actually have one. You can show that sigma z minus sigma z keep being the chiral operator. Okay, just like the previous one. So, I'm just trying to not walk you through the calculation, by basically imitating a calculation that's easier to follow, which is the graphene calculation. Again, here you get the same thing, right? You have a wave function you can write generically, which has this form. So this is for the case of, this is for the case of in the confined phase. You can actually write down the wave function right away. Actually, this was known to basically, I think, for really old high energy literature also, because you were interested in stuff tied to basically those topological defects. Without the kappa, that would have been the solution. That's the solution they knew. This is the omega of R. Remember, that's your magnetic field dependent prefactor that protects everything. And then you have this exponential of something which is localized, the pair potential, just a radial integral of the pair potential. And the only thing that you do here, which is basically new in the confined phase, is that superflow. And you can actually find out that the entire effect of the superflow is in this prefactor plus minus kappa y, which is really cool, because that for kappa, when the kappa is less than basically delta, right, you see that this keeps on being a very good wave function. And this is basically, you still have the Majorana zero modes that are localized at the thing, except that they're blown away by this kappa because of this exponential prefactor. And you look at the decay rate along minus y, you will see that as you increase kappa, the decay rate would increase. In the perpendicular direction, you see that it essentially is unaffected. And in the opposite direction, you see that the decay rate goes, basically, sorry, decay rate basically increases in the negative direction, minus direction. Sorry, this minus y direction, you see that the decay rate, because the minus thing, that zoom thing is right in front of that in my screen. I'm trying to get it away. So the decay rate is negative. So you basically look at that magnitude of that actually decreases along minus y direction. Now you see that at along delta is equal to kappa in the K, right? You start basically your superflow is very strong. Something strange happens, right? You see, first of all, in the decay rate actually goes to 0. And at the same time, you see that something all strange happening in the other directions as well. Right, so that is the telltale signs of a delocalization transition. Our Majorana zero modes are no longer ones to be localized. Right, so now this is the thing that the question that I'm going to answer next. What happens for k is greater than delta? You all know the answer in a sense. Right, so the deconfined phase, but we want to do some analytical control over that. So this is the whole thing, right? The deconfined phase. You can write down the general form of the wave function as follows. Again, just like that, at every vortex, you have this z minus ci. You have this prefactor kappa y, and you have this thing omega of r, and then you have this u and v, those two electron and hole, essentially what remains of after some unitary transfer, heavy unitary transformations, what remains of that spin and electron hole components. So now this is the wave function that's is a general local solution. And then you can show that this u and v actually satisfies this simple, instead of, this simple equation. This is very much like a Dirac equation. And you can actually square this to give you Helmholtz equation, which is basically del squared u is equal to delta naught squared u. Right? And then you can get your v like that. So now this is all very easy, but the only problem is that you want to solve the Helmholtz equation in such a way. Remember, this kappa is now not anymore, k is so grown that actually your superflow is actually diverging in one direction. You have to have a solution that cures that. And this was actually done by my student with a heroic effort, Michał Pacholski. And together they kind of basically, you can actually solve this Helmholtz equation with the condition that actually it diverges in exactly the right way to cure this divergence over there. It turns out that analytically this can be done, and then you actually can get analytical solutions of this problem, right? So then there you go. So this is the analytical solution of Michał on the right, analytics to the right. And then numerics is basically getting this thing in a basically a computer with all the band structure and everything and solving it. Then gets you the local density of states. And you see that this is the vortex position. And of course, there is one other difference between the numerics and analytics. Analytics is for a double vortex, a single double vortex. Numerics is basically a lattice of double vortices. right? And then for some very interesting reason, we could get the double vortex analytical solution, but not the single vortex analytical solution. So if anybody here is feeling very strong mathematically, I would dearly love to see and wants a really nice challenge, analytical challenge, would really love to see a solution of this analytically for a single vortex. But anyhow, so even with the double vortex, you see that you get a very good condition, like you get all the essentials of the numerics and the analytics part. And in fact, this is a double vortex. It's like people who did basically optics and so on, they immediately looked at this and they said, oh, this is a double vortex, right? So you could actually immediately see by counting the branches up and the down on both sides, you can actually immediately see that this is a double vortex. So now this is the superposition of basically this, you remember this is of this form, you have this propagating waves in one direction, and then a decay that will exactly cancel your kappa. Remember, because of that, exactly cancel your superflow exponential divergence. So therefore, there's actually some lambda going in there. And then, so you want to multiply this epsilon kappa y and then get the whole thing integral. That's the question. And you see that for this to work, that your p squared must be the dominant p squared is basically your k squared, superfluid momentum minus delta squared. And that's the scale where you get this density oscillations. And that's the telltale sign of this delocalization transition. Okay, now if you have many vortices, I'm slightly running out of time. I don't want to, so there's something in the chat. Give a flat band. I'll come back to that actually. Let me finish the talk. So you have many vortices, you have these, and then you can actually turn that after the published paper, you can actually get the solution for the entire vortex lattice. And indeed, you can see that these effects on this here, that darkened piece, you can actually see that in your numerical thing as well. So now, after 2 decades, you basically, I've started with this picture, right? So this was a D wave, didn't do it, but with a very good idea by giants in our field, Gorko, Schrieffer, and Anderson. But you see that even when the idea gets shut down because it doesn't work for that particular material, it might actually work. If it is a very good idea, it will actually can come back, and it did. And it now we show that it works for a wild superconductor. And then, in fact, even in the case of now you can apply this also for a very physically accessible case of a topological insulator, a superconductor proximatized, and a vortex lattice. And this is how it looks like. So these are the energy levels. You see that they actually look very nice and flat. And these are the 0 lambda levels of this particular system. And you see that the first, second, third, and fourth, you can see them very nicely sitting there. And they see that you're mostly flat as you go away from the mu is equal to 0 point, sorry, at higher energies, not mu equal to 0. You see that they basically get the slight dispersion. Now you can ask yourself what happens with the chemical potential. You see that this chemical potential actually shifts your bands up and down, but it doesn't destroy the flatness. So this is kind of a very nice and cool feature. And then another thing is that here it is. So this is basically something that is accessible. The quantity that's directly accessible by scanning tunneling spectroscopy is the local density of states. You see that, remember, I told you that the local density of states would be, would be strongly dependent on what bias you put. Depending on that, you would be more resistant to electron or the whole part. You will see that this nice scaling of this oscillation, which given by the period h bar pi over q. And that q is, remember, is the value, this k squared minus delta squared, square root of that. And then you see that with that, you can see basically by looking at the Fourier transform of this, you can actually see that you actually, remember, this will not be a perfect lattice. You might have some, something actually destroys that perfect crystal structure. So you get some crazy loss of disorder around. Even then, you can actually see the telltale signs of this. That will be a signature of a Majorana phase transition, basically a phase transition, delocalization phase transition for Majorana that form a Majorana lambda level. So with that, I'm going to conclude and then come back to the question. So basically, what I talk about is that if you have a Cooper pair momentum with a superflow, if it is greater than your pair potential in in a topological superconductor, you actually can have a deconfinement transition from Majorana zero modes. Then a flat band appears protected by chiral symmetry and density of states oscillations. You get a density of states oscillations with wave vector P, which is given by k squared minus delta squared. And the stripe orientation, remember, determines the chirality. So you can actually see what sort of chiral source Majoranas you had by looking at the stripe structure. Now the question is, of course, now you get them delocalized. Can you braid them? So this is actually the part that I was hoping to also get to. There's also the dynamics part of this, but I would not. When I was preparing the talk, I realized I would not ever really get there really in a reasonable amount of time. But maybe in the future we will. I would love to or whoever is interested, I'd like to talk about it. So now you can get some dynamics from that, and then you can get some braiding, hopefully, and those are the things. And one other thing is the interactions. So we all know that those of you who, like, when you have a flat band, the effect of interactions basically get extenuated. Right? Even the weakest interactions can. Remember this twistronics, graphene, you know, all these graphene stuff actually comes in because you actually form, by twisting the graphene layers, you get flat bands, which then makes your interactions extremely important. Now we have a very interesting flat band of Majorana-based zero modes, right? The delocalized Majorana zero modes. Now, the question is, the interactions here might give you some very interesting stuff. You know, like among them, for instance, I would say that, for instance, if you have this Majorana fermions with 4 fermion interactions, would be a picture of a with random. I think it would be actually a model to understand black holes, and from that to actually maybe some other exotic physics might be hiding in these levels, which actually might be also very accessible by experiment. Well, I'm going to stop here. Thank you very much. Not over my time. Oops.
Thank you, Inanç. We have some time for discussion, questions, and so on. There's already one in the chat.
Yes, there was one in the chat. If you have a flat band, that means we have infinitely normalized mass for our quasi-particle. How we move quasi-particle infinite effective mass and assign a wave vector to it. Well, assigning the wave vector is easy because, you know, you can have any momentum, right? That's not. It's just when you have a flat band, you don't have velocity. So that's the key thing, and that actually is not something that we don't know. In a quantum Hall state, or lambda levels, you have that, right? If you look at the bulk system, right, that actually is so there's one, of course, to answer your question. One thing is that, right, if you make this of course, a finite system, that's finite zero modes would actually tend to come up and then form you some interesting looking edge states, which will be basically, which will have also a Majorana character, something that I'm basically would be very much interested. And so the wave vector is easy, and then the moving part is exactly as I said. So of course, once you have this at the edge, you start having a dispersion, and that actually moves it along the edge. You have the edge states. And the other thing is that what I envision is, you know, yeah, I guess, you know, basically you delocalize them, and then you might be able to manipulate them in that delocalized state. So that's the idea. Okay, so Şevval Taşdemir, how is the surface conducting vortexes formed? Is rotating the spin of the Majorana's fermions, and what is the main difference between Majorana's and wild fermions? Okay, so these are interesting questions. So now the wild fermions are basically massless. I mean, if you go from the, so okay, I will mainly answer it from the condensed matter point of view. But you know, also from the high energy thing, you look at the Dirac fermion, which basically means that we basically have a Dirac equation, and that Dirac equation, there's a reason that it has to be 4x4, right? So that's actually what you can actually think about it in the following, in a nutshell. When I think about a Weyl fermion in condensed matter context, remember, Weyl fermion in the condensed matter context is basically a three-dimensional graphene. You have p dot sigma in 2 dimensions for graphene. You have p dot sigma in 3 dimensions for a Weyl fermion. Okay. So now the thing is that, and then of course they don't come alone, right? That's the problem, because you cannot, you know, if you have a graphene with p dot sigma in the off diagonals, you can put some sort of ways of getting a mass I'm opening up a gap in that case. In the 3 dimensions, you see this, that's why sometimes called topological semi-metal, because whatever you do to this, if you have 2 bands, you have this, basically those bands touch at a single point in 3 dimensions, that touching is protected. In the sense that any perturbation you try to put on that, right, in that, and that involves those 2 bands, won't be able to open up a gap, right? It moves the position of that touching point around. So now, therefore, you must actually, the only way you can gap this, we know that we come from a gap thing, you have to have another Wald fermion coming in, and they come and annihilate each other, right? So you have the opposite chirality somewhere. So if you have these 2 opposite chiralities, the minimum model that you then may want to write is basically 4 bands, or in some way. And so that's why, kind of, in a sense, from the condensed matter way of explaining why Dirac, I mean, of course, Dirac had a much nicer argument, you all remember from your, relativist quantum mechanics courses, but from this context, you can see it like that. Now you have this mass and so on. So then you may want to say that, then this is kind of then you have a Wald semi-metal is when those, basically those, from the point of view of condensed matter physics, you have those cones, but they're separated in momentum space or in energy space, right? So you can actually isolate them and then do transport them. Those are Wald semi-metals. Now, Wald superconductors are the corresponding thing in a superconducting context. So they don't have, and just like you have the Wald basically Wald semi-metals are semi-metals, and then you have the topological insulators, which are insulators in the bulk. Right, then topological superconductors are insulators in the bulk. You have the Majorana surface states, whatnot. And Wald superconductors are the same thing, but then you have a basic, keep on having a basically quasi-particles in the spectrum. Okay. So now you look at those quasi-particles, they have this character that basically in this context, that you have a condition on that fermion that if that's those 2 bands are based, 2 atomities are formed by particle symmetry, is that you basically have one spinner is actually essentially is a particle hole conjugate of the other spinner. Okay, so that gives you some sort of realness on your wave functions, and it shows you that ultimately that's something that we discussed last week. You might remember, if I'm looking at the excitations, the excitations have the property that if you create a positive energy excitation at energy E, is the same as destroying a negative energy excitation at minus E. So that basically is the kind of outcome of this. That when we call is the Majorana fermions. Okay, in the context, sometimes they call this Majorana equation and so on. You basically have a 2x2. You have a real solutions of the Dirac equation, or another way of putting it, if you, instead of putting the usual Dirac mass, you have another type of actually introducing a mass that will protect this, structure that your upper, your 2 spinners, you have 2 pieces of your basically double spinners, right? So I'm using condensed matter language here again. So I apologize for for other audience. So you basically have the spinners of up part and the down part are related by based charge conjugation symmetry. So I hope that explained the main difference. So one is when we, at least in the condensed matter context, when we talk about fermions, we mean basically 3-dimensional graphene looking thing, P dot sigma. When we talk about Majoranas, we talk about superconductivity always, and have this condition gamma creating an electron at, or creating excitation at positive energy is destroying it at negative energy. Rotating surface conducting vortex is formed. So the surface conducting vortex, I assume what you mean is, so let me see. So basically, in the case of a superconductor, you have this based in so-called in type 2 superconductors, you have the so-called intermediate state, in which you have strong enough magnetic field that will start threading through the superconductor, right? So the superconductor cannot basically repel everything out, but it actually forms this nice little vortex lines that go through the superconductor, and basically these are basically called vortices. The fact that you actually form a lattice is due to Abrikoso. So this is basic, and there's also a nice story that he calculated the base to this. They formed the lattice, and then he calculated, I think, a square lattice instead of a triangular lattice and made fun of, I think, to no end by his colleagues. And I think he even kept on, kept publishing his results from a long time. So now basically that's how the superconducting vortex is formed, basically by the superconducting trying to repel the magnetic field, cannot repel it completely, so it just makes a region that it can actually thread through, and then basically tries to keep the superconductivity around it intact. And that gives you all this, circulating supercurrents and whatnot. The spin of the Majorana fermions, normally the spin of the Majorana fermions is, of course, is a little bit of a, I kind of glossed over that. And what I mean by spin is the following. So normally the spin is zero, right? I mean, especially if you're talking about Majorana zero modes here, not Majorana fermions. In that case, Majorana zero modes, the spin is zero. If you try to put a magnetic field, it will not change its energy. Right? If you had a spin, you always have a magnetic moment, and you have to. So that doesn't exist here. But what happens is that there's still, like you talk about, remember we were talking about, let's say, upspin electron and an upspin hole, basically is an equal superposition of an upspin electron and upspin hole, has zero spin, but because the whole spin is opposite. But nevertheless, you can say that it is something like some leftover spin left in this thing, right? Because the host electron is an upspin thing. And that type of spin, we might call topological spin, is the spin that, or the chirality in this case, that the superflow can distinguish. I don't know that answered the question.
Is there any more questions? It's a very exciting talk. Let's thank İnanç one more time.
Thank you very much.